Good morning, everybody, and nice to see so many of you here, even though it's a Saturday and we changed the building and all that. And we'll soon get going with two talks. Now the theme is like explaining quantum phenomena, and especially we've been focusing on the two-slit, and in the first talk also on the Stern-Gerlach. But let's begin with Peter van Reeth, who he actually used to be at Berkeley when David Bohm was there, and then you were studying with Basil Hiley, and for the past 10 years Peter and Basil did a lot of work exploring the quantum potential and simulations, and Basil was always extremely excited. You know, when I would meet him, he would show Peter's pictures, and he really liked the work you were doing, I must say that. Anyway, please.
Thank you, Pavel. Thank you, Pavel and Tomo, for inviting me. Can you hear this? Yeah, everybody? Good. So what I kept the old title that I get from a talk I gave a couple of 3 weeks ago, I think it was, in Oxford, which was more about Basil's life and work. And it was conversations with Basil, because I had a lot of conversations. We met up roughly twice a week, and then on Zoom and on the phone. And whatever we discussed, somehow the quantum potential kind of creeped in the discussion as either an explanation or something we kind of felt was relevant. Right. So the talk kind of overlaps a lot with what you've seen yesterday, but as we were talking with Mike, you know, the more you go over things, the shinier and the better your understanding hopefully will be. So Chris yesterday presented a lot of work similar to this, and he was kind of, as he explained yesterday, kind of the originator of this development of the Bohm work in the 80s, which he did with David Bohm and Basil. And I've been doing that with Basil and Vincenzo Monachello, who is now the person doing the experiment that Rob Flack was describing yesterday. So I'll discuss that. I got to show trajectories again. I'm interested in how these trajectories are related to the quantum potential. What it really means, this quantum potential, is still an open question, and I want to kind of open some kind of debate about that. And then we show that in two fundamental experiments in physics, which are kind of the two experiments one uses to not justify, but to explain why quantum mechanics has developed as it is. It's the kind of double-slit and the Stern-Gerlach experiment, yes, which highlighted the role of the interference. So the talk we had yesterday about particle-wave duality, in a way, and then the concept of spin, which is still kind of vague in a lot of people's head, in mine also sometimes, and the double. And so the aim here is to present you some results of these simulations, but then also to kind of relate this to potential experimental verifications or confirmations. And the reason is I feel that the Bohm approach has a phenomenal richness on its own, but to convince other physicists, it would be nice to kind of show something that you're never going to be able to convince 100%. But to show something where at least the questions become open, yeah? And people don't just put them aside and say, oh no, it doesn't exist, forget about it. And so that's the idea of the talk. At the end, I'll relate this work to something that was presented in May by Lyndon Neal, who talked about the DeWitt quantum potentials, for those who were there. So this is relating this work to curved space. So not general relativity, but just the curvature of space, a pseudo-Riemannian space. Right. So I'm going to repeat what a lot of people have said, but I really insist on it because there's a lot of confusion. The Bohmian approach says, let's consider the Schrödinger equation. And then just says, let's write the wave function that satisfies this Schrödinger equation in polar form. Yeah? Now, I don't know how many, because I know there's a mixture of philosophers and physicists. For a lot of people, if they've heard about complex numbers, they will have heard kind of z is equal to a plus ib, where you've got the real part and your imaginary part. Okay? So that's kind of standard way we introduce complex numbers. So for those who see, wait a minute, what is this? Well, we consider the wave function to be complex, and it can be shown in a formula that you can write it in this exponential form, e to the I something. Okay? So I'm just saying that because sometimes people are slightly confused, and it's a very important point. Because everything I do afterwards kind of relies on this form. Not that only this form will give you the results, I don't know, but the simplicity and the beauty of the results comes from using this polar form, okay? Because the mathematics kind of brings out the results in a much more neater way than if you use this form here. Right, so what Bohm did in his 1952 paper, which Chris mentioned yesterday several times, is he said, well, let's assume that this is the wave function, and at that point, you plug back into the Schrödinger equation, and you get two equations. Because if you rearrange this so that's equal to 0, the top equation, Schrödinger equation, then if you have a complex equation equal to 0, the real part and the imaginary part are 0 on their own. So you go through an exercise which is done in high school, and you get this imaginary and this real part. Now, the imaginary part is a continuity equation where you can kind of accept, in a way, that the psi squared, so the re to the is squared in complex modulus, will be equal to, therefore, r squared, and that's going to be some probability measure. So you've got this standard continuity equation, and then you've got the Hamilton-Jacobi equation that you have in standard classical mechanics, but you have an extra term. And that was kind of what I assume, because I never discussed it with him, must have kind of jumped out to David Bohm and said, wait a minute, we've got something really different than what we had before. And that quantum potential, we call it the quantum potential. It's kind of different from any other potential for the moment. It's non-local. It depends on the wave function. Yes? It's not something like 1 over r potential that we kind of are used to with a selectric or whatever. So it depends on the wave function, and the reason why we can call it a potential, it appears at the same level as the classical potential V. So, having done that, the important things to notice. The wave function isn't explicitly in these two equations, if you notice. There's only the R and S. So we're not going to solve these equations to find the wave function. Yeah? It's a different approach. We're accepting, and it's a very important point, that the Schrödinger equation will give us a wave function. What we're saying is that wave function will give us, if we express it as re to the is, these two quantities of the wave function, and these are going to be coupled because we have these two equations, but they will satisfy these two equations. Therefore, we have now kind of done something to the Schrödinger equation, looked at it differently, And you think, okay, well, it's very nice, but what have you done? Because, you just use the Schrödinger equation, you wrote it differently. And what we've done is, for me, we've kind of created, I call it the prism tools concepts, that allow us to analyze the quantum system differently than if we just looked at the wave function. What do we do with the wave function? Well, we square it and we find the probability of whatever we want to find the probability of. And I think for David and Basil, and maybe Chris can confirm that, Basil also used to say, the idea is having something more intuitive. Not intuitive in the simplistic sense, but he said that often he felt that for David Bohm, things, he had a feel for the physics. Yeah, I think it's a fair thing to say. He had that kind of gut feel that this has to be right. He said sometimes, he'd present something and Basil would say, but how did you get to this? I said, I feel it's right. Yeah, and you think, well, okay, I feel it also, but it's wrong most of the time. Anyway, so what he does, what you get is this quantum potential, and then there's been an evolution in the thinking of this. In the first paper, Bohm associated the S with the action. As I'll show you later, there is something else that one can kind of use to define this, what's called a local potential velocity. And this local velocity is a very important concept, because in quantum mechanics, as you've been told several times yesterday, you can't associate a particle with a point in space and a velocity to that particle. So there's no locality of the velocity. You can't say, this particle at this point has that velocity. David kind of proposed that, yes, there is. And if you have a velocity and you define that at some point you have an initial position, then you can propagate that like you do completely normally to get what's called a trajectory. Now we come back, and there were several discussions yesterday on the linguistics and the problem of the language we use in physics, and I think it's a very important point. Yeah? We are using the word trajectories in maybe a slightly looser way than exact classical trajectories for the moment. Because and we are also, sometimes the word flow lines comes into the language. And the reason for that is, in 1927, part of this explanation, proposal, that David Bohm did in 1952, Madelung had proposed a hydrodynamic kind of picture of quantum mechanics. Nobody was interested in it. De Bruij's work also was, it's kind of completely different in a way, but kind of based also, from as far as I can see, on these ideas. And a lot of the work here will be kind of hinted back to some hydrodynamical fluid, or kind of presence, in a way, in the underlying explanations. Yeah? And that's kind of a richness of the physics approach, is to kind of pick ideas here and there to kind of get an insight. Right, so we got this local velocity, which is very interesting, because we always say Bohmian approach is non-local, but we have a local velocity, whereas classical quantum, Copenhagen interpretation doesn't have a local velocity. So the locality is a kind of funny thing. Right, this is, that top expression is really a flow expression, a flux derivation, and very standard that you can approach, yes. But what you discover is that if you approach that and you do an extra step, which a lot of people don't do, which is you say, okay, but it's a complex quantity, I'm going to keep both parts. Which, very often people say just throw away the imaginary part. You're going to keep that imaginary part. You get back to your local velocity that we have used before, but then you've got also this, what I call amplitude velocity, but in the literature, especially Basil's and David's literature, it was called the osmotic velocity. The reason are a bit more complex, but it's because of a paper of Nelson in the 60s, who had a stochastic approach to quantum mechanics, where he kind of got that same idea. And I'll want to talk about that. That's an important point in the development here, because it plays a significant role. Right, this is kind of what it looks like. And notice it's opposite to the gradient. Yeah? So if you go on a simple Gaussian picture, the gradient is on the right-hand side is going down. Okay, so you have a negative gradient. We're taking the opposite, so it's flowing outward towards the positive values. And as R becomes smaller and smaller, R becomes smaller and smaller, your density becomes smaller and smaller. You're getting into the wings of your Gaussian. Well, this becomes larger and larger. Okay, so it becomes much more important. One has, and it's going to be 0 at the maximum because of the gradient being equal to 0 there. And therefore, you're going to kind of have something that is kind of controlling, in a way, this packet. It isn't related to explicitly, I would say, to the spreading of the wave packet. For those who know, in standard quantum mechanics, in general, a wave packet, if you just let it propagate in free space, will kind of spread out. This is not related to that explicitly. I mean, all of these things that we are not. Right, so a bit of the formulation here. We start off with our RE to the IS, and as Chris explained yesterday, we just assume, for simplicity, 2 wave packets at each slit. Yeah? You can do more complex, have a beam coming in. At the end of the day, the results are nearly 100% the same. Now, the key point here, and don't worry too much about that, the kind of the details, but the key point here is we have our 2 wave packets, but we want one picture. We want one wave function for the whole system. Yes? We've got there's no use of just letting the 2 wave packets independently. We want one, and that's what creates the interesting stuff. So that the whole wave function will be our RE to the IS, and the R and the S will depend in a slightly messy way, but kind of not dramatic way, on the 2 wave packets that you start off with. Good. So you got this, and then you express the velocities using the standard approach, and you find that you have an overall Bohm velocity and an overall osmotic velocity. When I see overall, we have 2 wave packets, but the particle is in A or B. You agree? So this is saying some particle at a certain position has come in through one of the slits, and its velocity will depend on combinations of the potential velocities if it had gone on its own through one of the slits or the other. So this shows how the 2 slits are kind of correlated, are kind of interdependent. Yeah? But what's neat here is it's a very kind of clean relationship between this kind of, and it's a partly, I feel, some kind of non-locality, because it's kind of bringing in the potentialities of the 2 slits, even though there's no particle. When I evaluate VB, that particle, that object entity that I've evaluated VB for, could have gone through A or B. Yeah? But that's irrelevant. The overall picture is, had it come to A or B, it would have had these velocities on their own, and everything becomes kind of interdependent. Good. sorry. Right, so this is what it looks like. I mean, I've just put this because it's a 3D picture, always looks nice. But you've got the density at the top, so that's your standard kind of interference pattern. What we see in general in pictures of these are slices, vertical slices, yeah? And below, in blue, you have the zero plane, okay? And so what this shows, and unfortunately I could have done it a bit more dramatic, it shows that the local velocity increases as you go away. Yeah, you can see there's a bigger difference here. And at certain positions that has this kind of singularities. And these correspond to the valleys, the minima in your density plots. For the osmotic, what's interesting, you've got this same picture. It is completely, well, anti-symmetric, if I'm correct, along the zero axis. But you can see here, where we have a minima, how it kind of flows, goes up. You've got like a singularity, like, well, a tan behavior. Yeah? What this is happening is, these osmotic velocities, as you go down this slope here, increases dramatically, and where it is nearly zero, and don't forget, in this picture, it's nearly never zero, yeah? Because you have overlapping Gaussians, which never go to zero themselves. So automatically, there'll always be a probability of finding a particle here, and the velocity, that osmotic velocity will increase dramatically. Right, so that's to give you a picture of what these look like. Sorry, up. This is the standard picture that you would get. Yeah, I'm not going to go in details over it. Most people have seen it. So we get trajectories. Standard quantum mechanics tells us go over here, wherever this is showing. Thank you. Yeah, go over there, put your detector, and you'll see a nice picture. And as you come in, well, forget about it because it's a complete mess. So don't worry too much of what's happening here. What the Bohmian picture says is, well, here it's very difficult indeed, but what seems to be interesting is the particle can go off along a certain route and then fall off and join another kind of what I call sub-beams. I asked Chris yesterday, because he had discussions with David about this, and he doesn't remember David kind of jumping out or saying, this is weird, this is not correct, or this is wonderful, all these things. Yeah?
Yeah, I mean, he was very excited to see the trajectories.
Yeah.
He didn't comment specifically on the ones.
Yeah. Okay. So, but this is one of the interesting things. Okay. A lot of people would say, well, yes, okay, you got these trajectories, okay. But at the end of the day, things are exactly the same as before. So, you're never going to see anything. Well, God knows, maybe. Right. So this is what these trajectories look like on a density plot. Okay? So it's the same picture that you've seen several times and yesterday also. What I've done is slightly different. I've just put the projected in a way the trajectories on the density plot. So these ups and downs are not ups and downs in space, they're ups and downs in the probability space. Yeah? And what is interesting for me is, if you look at this here, these are what you would, if you go far away down here, what you would see on the detector. You agree? Now, on the detector, you would say the particle is, if there is a particle that has arrived here, because there's still discussions on that, but something has arrived here, and you do kind of a straight line to one of the slits, and you say it kind of gone through all that, through the space up to here. What this shows is, yes, these ones here will have done that, yeah, overall. But look at these ones. You have your highest probability of finding a particle here, but no particle is following that path. So even though the highest probability is to find a particle in that region, we are very close to the slits. Yes? What we have is, yes, there will be a lot of particles there, but there won't be, it doesn't mean that if you have a higher particle, a higher probability, the particles will flow along that kind of maximum. Right, so that's that. This is just to show you how animations have evolved since Chris has done it. I did this on my own, just a kind of, I tried to have an animation, I forgot about that. So these are the velocity vectors that I'm going to show for one trajectory. The blue lines are where asymptotically you would have a maxima, and the red lines where asymptotically you would have a minima. And I just show you a few examples here. So at this point, we're very close to a maxima. The green is the osmotic velocity, it's very small. And the particle is going up, so it has a significant positive velocity. You go further. Now in this case, the particle is nearly going flat, horizontal. So you have a small velocity. So we're getting in a region where we're going down kind of the density, the Gaussian, and we're going to get, if I've done this correctly, no, well, you can see this. Yeah, we're going to cross over a minima in the density plot, so you can see that the osmotic velocity flips over and becomes very large. And these are this tan kind of behavior that I showed previously. Right, so now let's look at the quantum potential. The quantum potential can be written several ways, and that's the original way of writing it. With a bit of mathematics, you can show that if you use this concept of the osmotic or the amplitude velocity, you can write it as a kind of kinetic energy term of this velocity, plus this extra term, which I haven't yet completely got my head around to. Because it's a derivative of a velocity, so if it was dt, you'd say it's an acceleration, but it's one of these quantum derivatives, a d by dx, which when we act on the wave function, we know what we're going to get, but here it's a bit more subtle, and I want to get a better picture of that. So I'll leave that for the moment. And this is the expression you get when you put everything together. Okay? Again, not important. As a matter of fact, it's wrong. There is something in there, a sign or something that I've got wrong. The simulations I'm going to show you haven't used this expression. I've used the original expression. So the three ways I could calculate this. Two agree, one disagrees. I've taken the two that agree. But again, this, like we had in the velocity, shows very well this kind of how the quantum potential for a particle at a position xt depends on the velocities, the potentiality of the velocities had it gone through A or B, and also the quantum potential that would have appeared had it gone only through A or only through B, i.e. the split, one split only open. And you've got all of the, so again, this kind of gives the feel of the non-locality. I'm not sure if it's the same non-locality. No, Chris disagrees. So, yeah. It's not the same non-locality as what happens in the EPR picture. That's for sure. Right. So this is the quantum potential that Chris showed you very much, and that was in the original paper when it looked very similar. Notice that on this scale, it's very sharp, and then seems to be very flat. Yeah. If you go into the kind of closer regions, you can see, and that's an important point because people say, "Oh, well, you're just representing another way the density." The density has this Gaussian behavior. The quantum potential doesn't have this Gaussian behavior. Now, the key point about this quantum potential, it does not depend, its action doesn't depend on its value. It's irrelevant. It can be 1, 1,000, 1 million. That's irrelevant. What's relevant is its change. Yeah? So the fact here, if you can see, yeah, that here the trajectories are nice and straightish, and here also, it's because the quantum potential, although it's a maximum, it's the biggest value it can get, it's not doing anything. Yeah? Because it's not changing. Where the changes occur are when you cross over these values. And you can see that the kinks that we were talking about earlier happen, these kinks here happen because of the action of the quantum potential, because this is where really the quantum potential becomes active in a way. So this kind of corresponds to very much what we were discussing already yesterday, and just shows you that this quantum potential has a bigger effect in explanatory effect, yes, than just looking at the density. If we accept this kind of locality of the particle picture, which a lot of people won't accept, but that comes, I'll come back to that later. Right, so the Stern-Gerlach experiment. Right, the second fundamental experiment in quantum physics, which has kind of thrown in the air partly this concept of spin that we've been kind of struggling with, you know, what is it exactly, and the mathematics that is associated with it. It's a very interesting experiment because if you look at the literature, Stern-Gerlach had this cigar-shaped picture, yeah, which you have to really believe it to what they, you know, and it was obvious for them what they saw, but it's still, nowadays it would not be kind of even a student showing that. You'd say, can't you do better? But they, you know, it was phenomenal what they managed to do. There were several experiments afterwards with hydrogen in the US and several other people, but not that many. And then after the 1935, nearly no experiment that redid simply the Stern-Gerlach in a very detailed, you know, proper way, but it was used all the time. Why? Because people said, well, you're going to use this to put yourself in a spin up or a spin down. So, you know, why worry what's happening? You have a machinery here, and it's used all the time at different levels. Right. So, I'm not going to go through this again. It's a nice exercise. What Bohm, Schiller, and Thurmer did is what they kind of related. They kind of accepted the concept of a spin vector. That's in space, and that's the, if you in space, you can use your Euler angles to define its position. Well, no, its orientation. Right. Then you write down your Pauli equation, so you get these kind of spinners, and this is what it looked like. Now this is called the flag angle. This would be kind of related to the azimuthal, and this would be your polar angle. Yeah, polar different from the polar decomposition that we've used in previously, that we're still going to use because, well, I've just said it here. Yeah, we're going to write this spinners as RE to the IS. And then we find that our Euler angles are going to be related to these different phases. And I've used just spin up and spin down, and related also to the amplitude of each part of the wave function. So that's interesting because it makes already the Euler angles are mixing the S and the R, and then your density becomes just this expression here, R squared and R minus squared with your coefficients. And if you go through the whole procedure, as they did in the paper, and Chris did in the paper where they first showed these behavior, you get an expression for the velocities, the Bohm velocity or the local velocity, and the amplitude velocity. The amplitude velocity stays completely the same. It depends only on on how the amplitude behaves. Although, don't forget, R depends on these angles also. Yeah, so things become more mixed. But you see that now, instead of having just grad S for the Bohm velocity, we have here. Thank you. Yeah, we have this expression where we're going to have the action really of how these angles change, which makes kind of sense in a way, yeah, because you're assuming that this vector changes in space, and that change of that vector in space is related to the velocity of the particle. Sorry. And you get this expression for the quantum potential. Again, as we had before, in the velocities, we have that kind of amplitude quantum potential, and then this quantum potential which gives rise to a torque. So, very much similar, except for naturally the angular part. Notice there's no psi dependence. So here the psi is this flag picture. So what people very often say, you have this vector in space, and you got like a little flag on it, and so this orientation of this flag has to be taken into account also. Yeah? But that doesn't come in this. And the expression for spin 1 and spin 1/2 are very similar in this picture. And this is what you get. So it's similar to what Rob Flack showed yesterday, but this is a spin 1. And what you have is the particles come out, you've kind of prepared them so that they all have a spin orientated horizontally. And then you put your detector at the end and you say, oh, I get spin up, spin down, spin 0, I'm happy, everything's perfect. And then somebody comes up and says, but wait a minute, how did it go from 0 to 1? And it's instantaneous, it is just. Now I have to remind you of something which kind of involves a bit more thinking and time. In the magnet, we do a very simple approximation. We say the magnet just gives a kick to the atom, and then once it leaves this magnetic field, it's kind of free. Yeah? So any evolution here is assumed to happen outside of a magnetic field. And what we're saying is, it isn't instantaneous. It's going to go smoothly up and become +1 or -1. So people will say, well, that's very interesting, but yeah, same thing for spin 1/2. It raises this question for the orthodox thinking. Yeah, are you going to go to only spin up and spin down? Yes, but how are you going to get there? They take time. There's no collapse at the exit of the magnet. Yes, if you put a very strong magnet and stay long enough with it, then it will come up, spin down. The interesting behavior occurs where there's no field or no gradient field present. That is true in the calculation, yeah? Because we can say there's no field there and that's it. Experimentally, that's very difficult. Yes? Experimentally, it's very difficult, it's nearly impossible to have a kind of clean cut. Therefore, getting a detector even very close would be very difficult, and the detector won't tell you very much about the spin. A standard detector will just say the particle has arrived here. It won't tell you what its spin is. So it's not a very straightforward experiment to do, and the orthodox interpretation, if you come back to here, in this region, they say, well, you know, your wave packets overlap. Yeah? So we can't say much. Right. So how much? How many?
A few minutes.
Oh, I only stopped it much later. No, but I have a lot to say. Right. Well, this is what we're going to be thinking about. Let's do, my aim personally is to, is to show, to have something that can be analyzed in such a way that the outcome is reasonably clear to at least start a discussion. Yeah? And this magnet picture is very important. Standard quantum mechanics says if you go up or down, red or blue, you put the second magnet, you organize it in such a way that they come back. Yeah, there's something in the between that's called the Humpty Dumpty picture, but that's different. Yeah. What you should get is the red crosses where and the blue crosses at a given point, and you'll get the spin red dot in the lower part and the spin blue in the upper part. Right. And this is what we calculate. And that calculation shows something completely different, but agrees totally with quantum mechanics, standard quantum mechanics. What it says is, yes, as you come out of the second magnet, you're going to be bent down. Everybody agrees on that. The important point of the Bohm approach is because you have a local velocity defined at a specific point, you can't have trajectories that cross. Because otherwise, for that, you'd need your local velocity to have two values, to be double valued or triple valued, whatever, for that to be defined. And therefore, the particle that would, in your head, you can imagine, comes to that point, doesn't know which way to go, in terms of the trajectories. So this says you can't cross this line. But then how does the spin kind of align itself with standard quantum mechanics, which wants you to cross? Well, what happens here in this picture that we have is as you go down here, the spins rotate from up to horizontal, if you want to call it, zero, and to down. So your detector here will say, yeah, well, you got what we expected. But in this region, not only has the spin rotated, but the velocities are all, the vertical velocities are all zero here. So these are the Bohm velocities. So that's really important because this is a picture that seems to say you're going to get something very different if, and only if, you can have a measure. If you put a detector here, standard quantum mechanics says, yeah, well, we predicted the same. You have plus and minus, and they all come out to zero. Yeah? Whereas we say, yes, that is your averaging, but if you go within. Now, I can't go into the details. Rob has mentioned a little bit of that. Vincenzo. So this is, you can see, not only do you see the rotation, but you kind of squeezing of the original spin zero. So even the spin zero are being affected. And you can, if you look back at the other picture, the spin zeros are taking back the value. The packet has kind of spread in a way, kind of aligned itself, and then being re-squeezed. Right, up, up. This is more dramatic when you put, so you change your condition, so you've got the spin at a certain angle. Not only this, but spins flip over from one branch to the other. Yeah? Now people would say, wait a minute, you've crossed the zero line here. The zero line is at 60 degrees downwards, yes, from the symmetry argument of what you started with. So there's no problem there. Right, good. So that is, hopefully, this is the quantum potential. I'll just show quickly a picture of the quantum potentials, yes. because I thought it was going to kick me. So we have this kind of behavior. You notice where there's a dramatic change is where you have this big increase in the quantum potential, and then it's just flat. There's nothing more to be done, yes? If the particle goes in a straight line, it's nearly Newtonian if you want to. You know, there's nothing there to change it. Right, and so these are other pictures. Sorry. Yeah, so for the experimentalists, I can talk about this privately afterwards on how we hope maybe to measure these things. Yeah, not directly the spin vectors, but the velocities. And it's a subtle argument, but it's kind of rather neat, right? This is so kind of the conclusions, which I've kind of mentioned during the talk. So what I find important in what I've shown is that these results show that there's a potentiality of making measurements which could confirm, not confirm, but could kind of give hints that there is something really important that's happening here, and that's different from what people expect. The experiments would be very difficult. Notice one thing, because a lot of people say that we're never going to measure the quantum potential. It's not the measurable. Yeah? We're measuring something which we explain the behavior through the behavior of the quantum potential. But the quantum potential itself is not the measurable. Okay? So that is thing. Then, do we need a collapse of the wave function in this picture? I don't think so, but that's still one of these wonderful debates of physics. This is the gentleman that I need to thank for it. That was all of this was done to Basil. But because I'm here in kind of relativity, I've got 2-3 slides which I put in on last Tuesday, 2-3 days ago. So for those who were there at the last meeting, there was a presentation by Lyndon Neal on a paper in 1952 that was written by Bryce DeWitt. And Bryce DeWitt, became famous for the many worlds, I think, and so many things in general relativity and quantum physics. And he had written this paper in the same volume that Basil had written his paper. And, Bohm. Bohm. Basil was still a little boy. Basil had written his paper, and that paper said, oh, there is a quantum potential also. Neither of them were aware. Basil said that he never discussed this with Bohm, and Bohm had never mentioned, and they're talking about Bryce DeWitt in other contexts, I'm sure. I think Basil had even met him. Right. So what he's done, and I can't go into details here, that he said, okay, really what he did was he said, I'm going to go to a curved space, but I'm not going to use the covariant derivative for my momentum. I'm not going to replace d by dx by the covariant derivative because I don't trust that. I don't think it's the correct thing. The Schrödinger equation won't be covariantly invariant. So I can't here show exactly how he did this, but he said, okay, let's look at the two-point transformations, go through kind of a solid exercise, which he didn't do in that paper, he did in a later paper, although he abandoned this project completely. And he said, you have to replace it with this. So people say, well, it's exactly the same as the covariant derivative. Well, there's subtle things. I think there's the minus, the 1/2, yeah? And the Christoffel symbol in the curly brackets is what's called a contracted Christoffel symbol. So you don't have three different indices, you have two of them the same. And you go through that. Now, what Bryce DeWitt called his quantum potential is wrong. Don't tell anybody. But it is fundamentally, he was right in a way. What he did is he said, well, what I'm going to do is I'm going to use the standard covariant derivative, i.e. kind of a classical covariant derivative, operate with my Hamiltonian, see what I get. Then I'm going to do the same with this P bar, which is my quantum covariant, or my covariant derivative, and see what happens. And he did that, and it's a little exercise that shows that you can write the differences. I would call it, therefore, more a correction term between using the wrong covariant derivative and this quantum covariant derivative. And he called that his quantum potential. So that was, Basil was very excited about that. Thought, wait, quantum potential, what does he mean? But it is, so I thought, wait a minute, it's just the difference between the two, why get excited? And then, just because when we were writing up the paper, we got to this point where we said, let's do a Bohm approach, RE to the IS, put that in with the Price-DeWitt covariant derivative. No, why not? And everything works out as before. You do get your real and your imaginary parts. You get the DeWitt difference, because that's what should be there. Yeah? So in a way, what we've done is it's like we've used the standard covariant derivative and done the correction. I mean, it's just a shorthand notation for this long expression. But then what I found was really interesting, and that was in the last few days, was these two extra terms here. This term and that term. So in this curved space, your two Hamiltonian, Jacobian, your continuity equations are changed by terms that are related to the Bohm and the osmotic velocities. And that's really, for me, a rather key. I haven't yet, it's just kind of brand new. What is important on here is that this seems to link the curvature with these velocities, because we have these, the Christoffel symbols are simply kind of a mixture of the gradients of the GIs, GIJs, kind of. So I think there's something rather subtle happening there. I don't know yet what it is. This is not relativity. Yeah? It's Schrödinger equation, but in a curved space. What does it mean? I don't know yet, but I think it has some kind of, maybe some insight that you would be interested in. All of this and other papers will be published. I'm just putting a bit of a, in proceedings of the symposium of Basil Hiley early next year. Thank you very much. Thank you. Back,
purpose is to have the discussion. So anybody have a question? Chris?
Yeah, so this bounce behavior.
Yeah.
Obviously you get that without spins as well, as I'd shown in my thesis back in whenever it was, 80-something. But, from the orthodox approach, I think that, the fact that people would say that because this detector is pointing at that slit, therefore the particle must have come from there, is actually, if you're a true Bohrian, you shouldn't even make this statement. Because there's nothing, you can't say anything at all. And also, if you calculate the current, just the standard quantum mechanical current, then that is also zero along that line. So
I took that slide away, but I was going to show it because it's something we showed with Basil indeed, and I'm sure you spoke about it before. Standard quantum mechanics
shouldn't say
contradicts itself. I mean, this was Scully and Englert and people like that who published this to show that these trajectories are not real.
Yeah, and we wrote a rebuttal of that, that paper. some time ago. And I mean, also those, the spin turning, as I'm sure you remember, was also shown in the paper we did on the neutron interferometry with spin particles, where you twist the spin in one of the arms, and then you get exactly this. At the output, you get exactly all those twisting velocities. And I've got a movie of that, actually, if you'd like to see it.
Okay.
Yeah.
Yeah, no, I think there's a lot there that you've done, and and there's a potentiality in these things. Here, the advantage of the Stern-Gerlach for the moment, as far as I understand, within the context of what's happening at the weak value measurements at the UCL, is, and I didn't explain that, there is a potentiality of measuring the velocities.
Yeah, I mean, you can use the weak measurement techniques on just to measure the velocities, and then I think it's a bit of a stretch to say you're then measuring the quantum potential, because you're measuring the changes of velocities, which you could say, oh, that's coming from the quantum potential.
Yeah, so,
but then there's a whole school
I don't know, experimentally, do you ever measure the Coulomb potential? Or do you measure the effect
No,
of the
exactly.
Coulomb potential?
Yeah,
I mean, that's a potentiality. It's called potentiality for a good reason.
Yeah. So then this is the choice that you get between those two versions of the de Broglie-Bohm theory, which I spoke about.
Yeah.
One which has the potential, and the other one which just says, no, these all we actually need is the velocity equation, and so in a way, if you want to think in terms of forces at all, you'd have some kind of Aristotelian force, which Newtonian forces cause accelerations, but Aristotelian force would cause velocity, and so it's a very different way of thinking.
Yeah.
And,
I mean, I went down the quantum potential because I think it's just, as I said, for me, the whole exercise is look at the problem with different glasses.
Yeah, I agree, and I think the quantum potential is more fun.
It's more fun, and it has a get. I mean, it's more intuitive in a way, It's just this, it's there.
Yeah.
That's the problem that I have with a lot of people criticizing it. It comes out, and it's not added ad hoc.
Yes, this is definitely the case. And if you've got your new kind of Newtonian hat on, then you like the quantum potential.
Yeah.
But if you're more Aristotelian, then you would say,
I don't go
you don't go down there. Anyway.
We are running a little bit short of time, so maybe we can leave some of the questions to the panel as well.
Sure.
And let's move on.